let's start with the very simple class of the solver, that is a sonic form. Okay, and so many paper people wrote with the sonic form. Okay, so if you look at the literature, you will find couple of the very nice paper or the report that mention about the sonic form. So let's explore first the laminar class of the test case. Okay, here I have a two test case. One is the shock tube, said normally we see in the in the compressible domain. So now so many people look at the shock tube is very good validation test case to validate their solver and all these things. So let's talk about first the backward facing step. Okay, so let's create the environment, go there. Okay, we're going to work with the release version. If you want, you can work with the extended version, but couple of changes you have to make in the test setup. Okay, so let's look at this. So first let me clean the case. Okay, and then let's look at the block mesh. Okay. Paraform, so try to check our domain how it look like. Okay, so this is the backward facing step. Okay, and this is very simple mesh size we are using. Okay, and let's look at the inlet plane. So this is the inlet plane. Okay, then we have outlet plane here. Okay, then bottom wall is this. Okay, top wall is this. Okay, then obstacle is here, entire thing. Okay, so this is how our domain is look like. Okay, so inlet, outlet, and certain obstacles we have. Okay, so and so it is a backward facing steps. Okay, so inlet, and then we have some class of obstacles. So that is when there is a obstacles, so there is chance that we have to see certain type of the shock creation over on certain places. Okay, so let's observe few more entries. So go here, let's look at all the conditions. Okay, so at the inlet we specify the 3 meter per second as a velocity. Okay, and then top bottom. Okay, obstacle we have only, and the top and bottom we say is a symmetric class of the plane. Okay, then outlet we say zero gradient. Okay, you can go with the wave transmissive class of the things as well. Okay, temperature, incoming temperature is 1. Okay, pressure. Okay, so we also specified sorry, it is about the outlet pressure. Okay, so you will see here we also say it is a 1. Okay, and then for the outlet, for pressure waves, it's supposed to pass through very neatly, so we specify this. Okay, okay, and L infinity is 3, and the value as a far field is something like a 3. Okay, so let's go back here. Okay, and let's observe the domain size first. Okay, so look, far field is 3 in the absolute unit away. Okay, so that is what we mention here. Okay, and at there we say uniform 1 value. Okay, so that is what we are specifying, and field infinity is also 1. Okay, and then gamma value and psi, how you want to calculate the pressure. So based on the psi, so psi we calculated from inside, and from that we try to calculate the pressure. Okay, so based on that it try to mimic the pressure calculation. So psi is nothing but the compressibility, so from the compressibility we have to calculate the pressure. Okay, based on the density. So that is what we are looking at from this. Okay, now look at the thermophysical property what we are using. Okay, so thermophysical property and turbulence property. So turbulence we are working with laminar. Thermophysical, what we have, He, psi thermo, pure mixture. Transport is the constant, H constant, perfect gas, species, and sensible internal energy. Okay, so species, this is molecular weight, everything given. Thermodynamic property, Cp, and the transport is the purely H constant. Okay, so for that we required mu and Pr, that is what we specified here. Okay, so now let's try to solve this. Okay, class of the flows. So before that also look at the setting in the system folder. Okay, so we are sonic form. Okay, and we are working with the delta t 0.002. Okay, FV scheme, Eulerian, and we are working with the Gaussian limited linear schemes. Okay. Then solution algorithm, we are working with the smooth algorithm. You can go with the BiCG and all this thing. Okay. And outer corrector is 2, inner corrector 1, and grid is orthogonal. No need to go for the non-orthogonal corrections. Okay. So this is very simple setting. Now let's look at the run. Okay. So what is happening, we gave the 2 pimple loops. So in each loop we try to solve first velocity equations, then energy, then pressure, okay, then rho. Okay. So this is all happening. Okay. Let's now look at the paraform and have an idea what exactly happening. Okay. So let's try to see the u value. Okay, so this is how we can see the oblique shock is created. Okay, here refresh. Okay, so depending on the our property, okay, it try to generate, and we top and bottom we gave the symmetric conditions. Okay, so this is why we will see this as a some very big obstacle of this size. Okay, and flow is passing over to that obstacle. Okay, so that's why you will see this class of the wave. Okay, so this is how the very nice shock wave is created over it. Okay, so then let's look at the some changes in the properties. Okay, so this is in the y direction, so let me see. Okay, okay, in the x direction, so this is how we can see the different change. Okay, so this is how u magnitude change over this one line. Okay, so if I show you how the line look like, it is something like a this way. So here I draw the line, and over that line I am seeing the change in the property. And what I am observing right now is the velocity magnitude. Okay, and then we have a pressure as well, how pressure is changing. If you want, you can activate the temperature from here, and then from here you can see the temperature variation as well. Okay, so at the shock you have an immediate jump. Okay, that is what you can observe from this. Okay, so at the shock you have immediate jump in all the properties. Okay, so that is exactly happening at these locations. Okay, we have immediately sharp change in the property above and the below of the things. So this is velocity, this is the temperature. Okay, so we have low temperature and then we have a high temperature. Okay, and velocity wise we high velocity and going toward the low velocity. Okay, as well as the pressure wise we have a low pressure and going toward the higher pressure at that locations. Okay, so this is how one can see very simple test case and setup. Okay, let's observe couple of few more test cases here. Okay, so let's go to next test case where we talk about the shock tube. Okay, so let me clean the area first. Okay, then we try to look at, so let's look at this area. Okay, so shock tube, is there, and first just look at how the test cases look like. Okay, so for that let me go to first that area. So let's clean the case first. Okay, then let's say talk about the block mesh first. Okay, so this is very simple block mesh, but what we're going to do here, we are creating certain sets. Okay, over it. So first have an idea what is the domain size and how the mesh is look like. It is something like a 1D flow. Okay, and what exactly we want to set a different property in the different zone. That is what we're going to do. Okay, so for that let's say activate this our axis, so it gives us the idea what exactly happening. Okay, so let's say this is our axis. Now we want to work with the set field, so for that we have a set field dict file. Okay, so look, we say the default values like volume vector field, that is u equal to 0 0, so everywhere it's supposed to be 0 0. volume scalar field temperature equal to 348.343, volume scalar field pressure equal to this much. Okay, then we say patch now with the box to size 0 to 5. Okay, so 0 till 5 we can patching with the different value. So what value we are saying? We say field variable temperature, we say it's low. Okay, and the pressure we are decreasing with one order. Okay, so that is how we are patching this area. Okay, so let first look at it. Set field. Okay, so it patch, and now again go back to the paraform and have a feeling what exactly happened there. Okay, apply. If you see here, velocity is same everywhere, but if you see the temperature, we patch. Okay, so in this zone we have low temperature, in this zone we have a high temperature, and then we have a pressure wise also high and low pressure. Okay, so this is how we artificially divide the entire domain into part, where one is the high pressure zone, high temperature zone, low pressure zone, low temperature zone, and then we try to release or this barrier. Okay, so and when the barrier is released, it means that in one side there is high pressurized fluid, another side there is a low pressurized fluid. So this fluid try to move in the this directions. Okay, and during that time this discontinuity, it also try to oscillate or try to move in the downstream direction. So that is what we're going to observe, and this is nothing but the exactly the at a shock level. Okay, so that's why it's called the shock tube. This is the tendency of the shock. From one side you have a different value, and immediately on the other side you have a different value. Okay, so that is exactly what we can see from this initializations. Okay, so now let's run this test case. Okay, so we initialize it, and again let's run this test case. But before that, check what is the mesh size I used. Okay, because if you want to capture the shock properly, then your mesh size is also supposed to be up to date. Okay, so right now I'm working with the 100 by 100 cell. Okay, you can increase the cell size and check how nicely you are capturing the shock. Okay, so that is the idea. So let's first run with the very coarse mesh. Okay, then we go towards the finer and finer mesh. Okay, so we run for a very small time. Okay, apply. Let's activate all the properties. Okay, and check for, let's say, temperature. So look, temperature is going in this directions. Okay, and then we have velocity we generated because of that. Okay, and the velocity what we get is something like 293 okay meter per second, and here is the pressure, how the pressure is diffusing and the velocity is increasing. Okay, but idea is that let's try to run for, let's say, another mesh as well. Okay, so this is, let's say, case 1. Okay, and what we observe is for a very coarse mesh. So what I'm saying, let's say create the folder as a case 1. Okay, and let me copy everything there. Okay, then I say, let's say case 2. Okay, here we have a case 2, but what we're going to do this time, everything is let it be fine. Okay, but what we want finer mesh. That is the idea. Okay, so what we required the finer mesh. So let's go with the 1000 element in the x directions. Okay, and when we are doing that, so let's case 2. Okay, we are here, and let's say all clean. Okay, now let's block mesh first. Okay, so mesh is constructed. Now say cp, we have to, okay, what we required, we place this original file into the 0 folder, because in 0 folder we already initialize it. Okay, in the first place. Now okay, minus r. Okay, so that is what we did. Okay, now let's say set field. Okay, so let me show you the mesh how exactly look like. Okay, so this is what we have. Sorry, yeah, So this is how very fine mesh we applied. Okay, and now just check the our discontinuity. Okay, so here is the temperature, so we have a very sharp layer. Okay, so this in previous case it is like a fainted type of the layer. Okay, and we have a u 0 and the pressure as well. Okay, now let's run this particular test case. Okay, okay, so look what happened, it didn't converge. Okay, so first understand, let me save it. Okay, so it started working, but after a certain time it stopped converging. Why? Because our delta t is very large for this fine mesh. So what you're supposed to do, you decrease the delta t first of all. Okay, if you want to make it converge, so that is the idea. Okay, so now we are going with a finer delta t, okay, as compared to that, and it going to work. So delta t play very nice role when you are capturing all the your shock and the quantity very nicely. Okay, at that time you require the very low delta t. Okay, now let's say it is done, so let's go and check exactly how the our all the properties is captured. Okay, then we try to compare both the things and have idea exactly how sharply we able to capture these things. So for that, let me copy this one file, okay, inside the case here as well. Okay, and then I can open the case number 2 also. Okay, so let me open the case number 1, sorry 2 is this case number 1. Okay, let's say apply, and here also let's activate everything. Okay, and check the temperature. Okay, so this is its temperature and this is this. Look, definitely it is a faded one. Okay, even though location looks similar, okay, but here it is little bit faded. Okay, so let's exactly quantify how it's look like. So let's look at the line plot over it. Okay, and line we go towards the x line, that is pass exactly from the center, apply it. Okay, so here is the line plot for first one. Okay, the similar line, let's generate the line plot for second one. Okay, and same way x, apply it. Okay, so look, here is the change you will see from both the cases. So when we have a very fine mesh, we try to capture the shock very neatly. Okay, but when we have a coarse mesh, it is like a diffuse class of the things. Okay, so the mesh play a very crucial role when we are talking about the this all the shock effect. Okay, so even you go for a much finer mesh and you will see very sharp gradient in it. Okay, so let's generate very quickly the third case. Okay, it's not going to take too much time, so no worry. Okay, let's say third case. Okay, and in the third case what we're going to do, we going to generate even much finer mesh. Okay, so as compared to this one, here I gave 1000, let me give me something like a 10,000 element in that direction. Okay, 10k, fine, save. Okay, so again go to that area, third. Okay, that type all clean. Okay, block mesh. Okay, now cp minus r .org we have to replace. Okay, okay, then set field. Okay, now run the sonic foam. Okay, it's not going to work because again we have to work with the delta t first. Okay, so let me change the delta t as well here. Okay, so delta t I required maybe much finer. Okay, fine, so it is working. Okay, it only happen that it will take little bit time. Okay, but no worry. Meanwhile what we do, we try to set the both the other test case. Okay, so OF other test case, that means we are read that file inside the para form. Okay, that is the idea. Okay, so here we have this one, so I say cp of this file, okay, into case 2 here, this is this one, then cp of this file as a case 3 file here, okay, and move this file to 1. Okay, now paraform, apply, go at the last. So this is the first one, okay, we have. Okay, so let's see how exactly it look like. Okay. Then let's read the next one. Sorry, case number 2. Okay, apply, this is second one, also activate all the variables, check the temperature, this first one, second one. Okay, let me check about the third one, what is the status, is reached till 0.03 only. Okay, so but anyway we try to read that file and be ready with that. Okay, apply, read this. Okay, and now let's look at the temperature field, how it look like. So it is at a third. Okay, so 1, 2 and 3. So look at 1, 2, 3, 1, 2, 3. Okay, so look, till it is a big sharp change you observe. Okay, so let look at here with the help of the line. Okay, x, apply, then here filter, recent one, x, this is second one. Okay, and then we have a filter, recent one, and the last one, and this is the third one. So look, so when we go from here to here, you will see very small change is appear. That means this is almost we are going towards grid independency. Okay, so further we refine the mesh, we hardly see any much more difference in this area. Okay, so this is how one can check in this area, it is hardly changing. Look, that much change is appear. Here in case of this, the sharp corner is doesn't resolve, but here it's we able to resolve the sharp corner. Okay, so this is the how one can check the scenario what is happening. So this is the how shock is propagated, and the property is the temperature is changing. Okay, only you can see only one thing from here. Same way, just switch off this. Okay, sorry, so we are looking at some different thing. Okay, so wait a minute, this 2, fine. So this is grid number 1, then 2, and then third one. Okay, so anyway, but it hardly changing from in this side. Okay, this is about the temperature. Okay, so in the similar line, okay, first look at how it is varying. Okay, then also go here and let's say refresh it, how far we went. We almost reached the yeah, for everything third, no problem. Okay, fine. So this is about the temperature. If you want to look at the pressure, okay, just see how the pressure is look like. This is about the pressure. Okay, so this is about the pressure. Then you can check about the u as well. Okay, how the velocity is changing. Okay, this is about the u. Okay, so at the beginning and slowly velocity is built up. Okay, so this is very simple test case, and you will see so many times people do the validation with the help of this very simple test case. Okay, so but it is a very effective test case to mimic the shock. Okay, so that is the normal shock. Okay, why normal shock? In normal to the flow directions. Okay, so that is why it's called the normal shock. Okay, so this is again very simple test case what we have here. Okay, Now let's also look at the, this is laminar based test case we look at. Okay, also look at the runs based test case. Okay, when we talk about the runs based test case, here we have a Naka aerofoil. I already solved this test case because taking longer time, okay, to show you certain things. So let me quickly give you the idea how the test case is look like. Okay, so first look at here. So we are working with the block mesh and the sonic form. Okay, so let's say we generated the mesh. Okay, so have a quick view of the mesh, how the mesh is look like. Okay, so this is a some class of the aerofoil. Okay, and what we are doing, we are changing the angle of attack. Either you change the angle of attack by changing the geometry and retain the flow direction as a parallel to the x-axis, or you can change the flow direction like this way and change the angle of attack. Okay, so that is the idea. Now mesh size, we have pretty fine mesh in this area. Okay, so that is what we have at present here in this direction. Okay, now let's try to look at the result, because I already simulated it. Okay, so when you solve it, okay, before we go for solution, just look at the all the entries. So before we go towards that, let's look at the constant folder and both these files. Okay, so we are working with the runs model and Lender's and Sharma's K epsilon model we are using. Okay, and physical property wise, we are working with the H constant. Okay, transport is a constant. Okay, so that's why we have a mu and the PR. Okay, so that is what we require. Okay, if you set mu equal to 0, you're going to work something like the inviscid class of the fluids. Okay, so that exactly what we seen in the previous case, not in the but in the backward facing step. Okay, where we set mu equal to 0. Okay, so if you didn't observe, okay, then please check, there is a mu equal to 0 in that case. Okay. Then we are working with the equation of state as a perfect gas equations. Okay, and now let's go toward the its boundary condition area and have a idea about it. Okay, so we are specifying at the inlet supersonic free stream velocity. We are specifying the P inlet equal to this, T infinity at this, and the U infinity in terms of this component. Why in the component? Because if you look at what happened, okay, sorry. So if you look at it is inclined, that surface. Okay, that means this is inclined, it not parallel to the x-axis, the entire domain. So we want this, let me show you the inlet. Okay, so this is the entire domain and behave as a inlet. Okay, and on this what we are saying, any places, okay, if the velocity is entering in this direction, that is the idea. Okay, so that is inlet and this is the outlet portion, that much. Okay, then we have a symmetry plane. Okay, this both the side we say it is a symmetric plane. Okay, and wall is nothing but this aerofoil behave as a wall. Okay, so here we specify at a supersonic free stream velocity, so far away from the object. This is the conditions. Okay, so that is what exactly we specify at the outlet, inlet outlet we specify for velocity. Temperature everywhere 300 Kelvin. Okay, pressure we say at the outlet transonic pressure. Okay, gamma L infinity. Okay, and then 1.3. Okay, so now look, now we don't have everywhere the same values. So let me see something like this way. If you see like this way, okay, and let me open this axis file. Okay, so if you look at everywhere as compared to this obstacle, okay, we don't see the constant distance of this outlet patch. Okay, everywhere it is changing. Okay, so that is the scenario. Then we don't have a common length. Okay, so at that point of time we are saying, okay, L infinity something like 1. Okay, then we have a infinity pressure we specified. Okay, and this is all setting remains same. Then nu T turbulent viscosity we say calculated, and at the wall of the aerofoil we say nu T K wall functions we going to use. Same way K KQR wall function we are using, and for epsilon also epsilon wall function we are using. Okay, so that is how we set a test case. Okay, now let me quickly show you the result, how exactly it's look like. Okay, so let's look at the result here. Okay, so what we see, we let's say start with the velocity. Okay, let me first rescale it and let me zoom in this area. Okay, so when the flow is approaching, okay, what's going to happen, just see. Okay, slowly the shock, it is called the oblique shock, it is developing. Okay, and at the back side you will see the nice shading. Okay, so that is what you will see in this domain. Look, okay, so vertex shading here, but idea is that in this location you will see the sharp change in the property, not only in velocity. If you look at the pressure, okay, you will see the sharp change in the pressure, you will see the temperature, you will see the sharp change in the temperature. Okay, so temperature going to reach how much, 55 T, 555K. Okay, same way if you look at the velocity, okay, velocity is reached something like how much, 794, so almost the crossing the Mach number. Okay, so if you want to check about the Mach number, you can use very nice utility here as well. Okay, let me, I not exactly remember the name of that utility post processing. Okay, then velocity field, okay, capital is there. Okay, okay, Mach, if you see, we try to generate the Mach number for each and every backup file what we have. Okay, so Mach number is almost reaching 2.97. okay, now if you go for post processing, we will see the Mach number as well. Okay, so here we have Mach number, and now let's look at about the Mach number and go at the end. Look, this is the value about the Mach number. Okay, so here is the almost near to the 1. Okay, and from there we have a sudden change, okay, in the Mach number. Okay, and in this area again you have oblique shock, okay, where again you have a sharp change. Okay, it is going to, that is what happening here. Okay, now let me show you the, let's say first, okay, let me first cut up the plane. Okay, exactly mid plane we have. Okay, now let's look at the vector plot over it. So this is what we have at present, this direction. Okay, so this is how the vector plot is look like over in this zone. Okay, now let me quickly look at the certain values over a line. Okay, so what I want on the x-axis. Okay, and I am what is the location of y point, something like, so it is something like 0.21. okay, so let me look at the y. Okay, let's say y or x is 0.021. Okay, so over this let's see how exactly the variation of different property look like. Okay, so let me check. Okay, sorry, somewhere I mess up. Same, yeah. Okay, it is a z normal. Okay, so this is fine. Now over this we are seeing all the property. Okay, something went wrong. Okay, fine, it's passing through perfect area. Okay, wait a minute, let me do it again, somewhere I mess up. Fine, now let's do it again. Okay, so we want to observe the certain property over a certain lines. Okay, I want over the x-axis and supposed to be 0.021 1. Okay, apply it. Okay, then switch off everything, just look at the pressure. So here if you see in this location, okay, so we have a sharp variations, okay, in that particular locations, okay, in this area. So here you will see the sharp change in the pressure value. Okay, so now let me see about the temperature as well. Okay, so temperature, okay, so temperature at, so let me show you here temperature, so it gives us the better idea. Okay, so here we have a temperature. So look, temperature at after this shock immediately increasing. Okay, so this is the location. So after the shock immediately the temperature is shoot up. So exactly we see that value from this. Now let's see the velocity and see the velocity from this area. Okay, so magnitude velocity, look, immediately it dropped down. Okay, and then see the here the Mach number now. Okay, so Mach number if you see it's immediately drop down. Okay, so that is what exactly we going to see here. So Mach number, okay, it is at a 1.77 and immediately drop down to this value lower in this zone. Okay, so that is what happened at these locations. Okay, so this is how you can look at the generation of shock with the very simple class of the test case. Okay, so this is about the sonic form, and we can generate the couple of shock wave with the help of these very simple tutorials.